Hi, this is Jason again, and we are looking at the fourth of a series of slides in Newtonian mechanics dealing with rotating reference frames. And the previous two, we looked at the Coriolis effect as well as the centrifugal acceleration effect, and we defined in the first one the nature of a rotating reference frame so that we could do those other two. Now we're going to round it out with the demonstration of how we know that the Earth is rotating using a Foucault pendulum. So a Foucault pendulum is simply a pendulum that is hanging from a very long, very stiff wire. So there's a heavy bob at the end and very long wire, and we're also making something that has a very long period for its oscillation. But it also has to not go very far. We want it to have a very small angle that it's changing through, so that when we actually see the pendulum bob going back and forth, it's not moving by much. It just has to be able to do this consistently for a very long period of time in order for you to see it. All right, so what is all this about? So let's look again at our equation that we derived in the first slide. It's the mass times the acceleration in the rotating reference frame is equal to the force, the real force, a Newtonian force that obeys all three Newton's laws. And the first one is the centrifugal acceleration, which is the second one, and then the third one is the Coriolis effect, which has the effect of things that are moving inside of a rotating reference frame. So what we're going to do is we're going to have some pendulum. It's going to have some kind of compact mass, so suspended from an extremely light cable, but that is stiff. It is not going to waggle or bend in the wind. And the pendulum is free to oscillate in any direction. It's not just on a hinge, it's not like a ball hinge or something, so it can go in any direction it needs to. And then the plane that it's oscillating in shall be normal to the Earth's surface, meaning straight up and down. If it's hanging straight without any orientation, it'll be just hanging straight up or down. The mass is then subject to only three forces. First, the force of gravity, which is directed always downward. Second, the tension in the cable, which is pulling upward. And third is the Coriolis force, which is due to the rotation of the Earth. So because of the equation of motion and mass in the reference frame that we're going to be looking at, we have a new equation that is shown below, which is we add the capital F then is replaced by mg plus t, and so those are our two forces. We are ignoring the centrifugal force in this analysis. So, just like in the previous videos, I broke it down into Cartesian coordinates inside the rotating reference frame of the Earth's surface. So we're doing this on the surface of the Earth, just like in the previous two videos. And we have the effective gravitational acceleration, which is g-tick, which is equal to the real gravitational acceleration plus the tension modified by the mass of the plumb bob. And then you subtract out the Coriolis effect. And once you break that down into the three Cartesian coordinates, x, y, and z, where x is pointed north, y is pointed west, and z is pointed straight up, we get these components for those three things. Notice there's an x and y and z component for the tension, but there's only a z component for the gravitational force, and the Coriolis force affects all of them. All right. So that messy thing can be collected and simplified as we see below. And so we are looking at specifically, because remember g-tick arrow is three components. It is x double dot, y double dot, and z double dot, where dot is the derivative with respect to time. So each of those things are the acceleration in the x direction is the first equation, acceleration in the y direction, acceleration in the g direction of the mass. So we are using the same kind of thing as we did before. This is just rewriting and making it prettier from the previous thing. And so v is going to be, like v sub x will be x dot, v sub y is y dot, and v sub z is z dot. So those dot notations make it a lot easier to write out. Okay, so now we go further and say, let's use some of our assumptions. We're going to now use those equations and try to simplify them so we can actually solve them, because those are tricky equations to solve. I mean, you can solve them directly numerically from there, but let's actually see if we can do some semi-analytical stuff and actually make some approximations to help us. The first thing we're going to assume is that the displacement of the swing of the pendulum is small. So it's not a big swing. We're not going to be swinging this thing back and forth. We're not going to be like the kid in the park who is trying to get the swing to go over the top of the bar. No, this is a very small swing. And so the length L is going to be very long compared to the distance R that we see in this diagram, comparatively speaking. So this triangle is actually pretty out of proportion. We want it to be very small angle. So that theta right there doesn't look big. It looks pretty big by comparison for what we're going to look at in reality. The vector R shows how far away and in what direction we're pushing the mass away from its rest position. Okay, so we can push it in any direction we want, but if we push it in the x direction, then our vector r tick will be x tick will be the same as x tick, which will be the same as L sine theta. So that would be true if we push it in the y direction. And if we push it off in some random angle, phi, then between the x and y axis, then theta itself wouldn't be affected. It's just the amount of x or y in the direction that we have. That's what that effective theta is. So if the displacement is small, then the angle of deflection is small, and therefore the magnitude of the r vector is approximately x. Let's say we're just keeping it in the x-plane. If the magnitude of the r vector is x tick, and that's equal to L sine theta, and if it's a small deflection, then sine theta is approximately theta. Remember, we're not measuring theta in degrees, we're measuring it in radians, so that's why we can use sine theta and just make it theta there. It doesn't work if you're doing it in degrees. The same would be true for y, and therefore we would have the order of magnitude of the displacement in x is like L theta, and the same is for y, so y is roughly y theta. But the displacement in z is much smaller because z tick is L minus L cos theta, which is on the order of L theta squared, because cosine of theta when theta is small is 1 plus, is roughly like 1 plus theta squared. So z tick, and we have to start from, we're saying the displacement is a little bit above because we don't have any displacement in x, but we do have some in z. So we have a very tiny displacement in z, which would be theta squared. So, but it's a small theta. Therefore, we're going to ignore all vertical displacements and set z tick to 0. That leads to the following things below. So sine of theta is roughly the magnitude of the r vector divided by the length of the line that goes down to the plumb bob. And therefore, we can actually, and x is equal to that. There's my theta, there's my phi thing, is the magnitude of r times cosine of phi, and there's y would be the magnitude of r cosine of phi. And so those are L sine theta, cos phi, and sine phi. But we're going to get rid of those really soon. I'm just making it there for completion purposes. Okay, so those are our actual values for x and y, where z value change is extremely small and we've ignored it. So now let's look at the tension. So the way we have is a tension diagram. So I've overlaid the tension force on top of that. And I've kind of ignored putting in the mass, the gravitational force, because I only have like so much space on my slides. So let's just keep going. Pretend like there's a g acceleration going straight down away from t cos theta. That would be the acceleration due to gravity downward. But that's not what we're worrying about right now. We're worried about the tension sections. So the vertical displacement is t cosine theta. And for small theta, again, that's t because of the nature of cosine. And so for the horizontal component, we get the following. So we've displaced it just a little bit, so we have t horizontal in some direction equals t sine theta times r tick divided by the magnitude of r tick. And that means what that thing in the r with r tick vector divided by magnitude r, which is, I guess I should have put a vector in there too, but that's just what we're trying to show with that latter part, with that latter ratio at the end, is that it's in the direction of r. right? So that's what we care about. We care about it being in the direction of the radial vector. So how do we then translate that? So it's approximately equal to t divided by L, because look, because we've previously defined sine of theta is equal to the magnitude of the r vector divided by L. But if we have the sine of theta divided by the magnitude, that's just basically 1 over L. So that's what I've done in the second part, where they make the roughly simulated so that it's roughly. Sine theta is still roughly that change, because we do have to take into account some way of saying, yeah, there's a little bit of a z displacement, but we're not too worried about that. So that's why I'm retaining the sim equals in that bottom equation just for completion purposes. And if that's the case, so it's t over L in the radial direction. Radial direction should have a little bit of a z component, but we're ignoring it for now. Okay, that's equal to t over L in the x component plus t over L in the y component. And that's how we would translate that out. So now we've got our horizontal components, and we can go all the way back up and put it all together. The equations of motion for the pendulum are now written below. X double dot, which is the derivative, which is the acceleration in the x direction in the rotating reference frame, is equal to T over Lm, which we had from before, times x tick plus 2 omega sine lambda. Lambda, of course, is the latitude from which we are measuring it, and omega is the magnitude of the angular speed of the rotation of the Earth. So, all right, so that's like 24 hours. It goes 2 pi radians, right? That's what that is. And then there's y dot tick, which is the velocity in the y direction. And so notice, because z, we've defined z to be 0, then z dot is 0 and z double dot is 0. So these equations have simplified quite a bit. So let's actually get even closer to this thing. So notice in the third equation we have the tension and gravity, and then we've got a small part which is the rotation and the latitude with the velocity in the rotating reference frame of y. So we're gonna do another little bit here and make one more assumption. We're going to note that the tension and the force of gravity are a much larger influence in general than on a plumb bob. So those two things combined are a much larger influence. Therefore, in the last equation, we're going to neglect the omega term, and we're going to get that the tension is approximately equal to mass times gravity. And that's about right? Because if we let it hang straight and true and there's no push to it, then that would certainly be true. So any change to that's going to be a very, very small thing. So let's go with that. Let's go with this. We could always just go through and plug this into a computer and let it chug. But if you did that, you're going to get a very small correction. I mean, you can. I mean, it's kind of there's nobody telling you can't. You can create your own Python script and just compile it and put the numbers in and see what you get. But you're going to find that it's not a very big effect. So this is an analytical way of saying, just because the computer is going to do it, it can do it, it could do it. Sure, we could have stopped at the very beginning and plugged all those things into a computer and said, I don't know which is big and small, and gotten out the answer. But if we use a little bit of judgment, like I'm doing right now, we can actually say, how close will we be? And the answer is really close, not far off at all. At the end. So let's continue. We'll say that t is approximated by mg, and we'll substitute that in, and we get the following thing in our equation. So we've substituted t equals mg into the equation. We got g over L in that instead of t over ml, right? So, and we've eliminated the last equation. So we only have an acceleration in the x direction and an acceleration in the y direction. We have no change in the z direction, which is kind of what we expected, right? So that's good. And so we're neglecting the last, we neglected that last term. That's our next step. And so we only have these two equations. Let's see what we can do to rearrange. In order to solve them as functions of time, we need to make use of some important relationships. So let's do the first thing. And notice that we're going to create a new variable, s. And s will be equal to x tick plus I y tick. And we can take the derivatives of each of those things, and they'll be derivatives of themselves like that. But I is the imaginary number, the square root of minus 1. All right, a lot of people will balk at that and say, why the heck are you doing that? I mean, that sounds like a pain in the tuchus. It isn't really. So let's actually see what these two equations look like if we do that. And they actually look a little bit better. So first we're going to substitute that value on the left-hand side, all three of those things, into the equations above and add them together. And that's the first line here. We got GL of x tick, and there's minus I GL y tick. So we see both of those things from the top two equations. And we have the 2 omega sine lambda y tick and the 2 minus 2I omega sine lambda x tick. So there's our first step. Now let's combine things together that are likes, and we see that, wait a second, we got a minus GL, that's an x plus y tick, and then we can extract those things out. We also have an x dot plus I dot. Oh, I shouldn't have a dot over that I. Whoops, that was a dumb thing. But it's an I dot, so why not? But it's a different dot than that. It's a dotted I, not a derivative with respect to I. I'm sorry about that, but it should just, wow, the typography there is very interesting, isn't it? Anyway, we're not too worried about that. So the first thing is going to be just simply s, and we're substitute s dot in for the last thing. Now that's actually really good, because now we have something we can use. We can now look for a sinusoidally varying solution to the last equation in this form, which is just the exponential e to the I minus I omega t, where s naught, which is the coefficient out front, is just some arbitrary complex constant. It'll be something else like a plus bi or what have you. And the omega is a real valued angular frequency of the oscillation. That's going to be what's really the oscillation we're going to experience for the plumb bob. That's important. We're finally getting at the frequency of the oscillation because that's a sinusoidally varying solution. So let's plug S now into this thing using these values. When you do that and take the derivative of this and then the second derivative, we get the following quadratic equation in omega. This is good. Quadratic equations are good. Why do we like quadratic equations? Because we can solve it in a normal way with our old friend that we used back in 10th grade, that we learned about the quadratic equation, and that's what I've done in the below. I've just basically used minus negative b plus or minus b squared minus 4ac, and that's what we've got, divided by 2a, and remember that old thing from grade school, that's what I just recited, and that's approximately equal to sine omega sine theta plus or minus gl. Why? Because we're eliminating anything that's omega squared, because that's small compared to g over l. So there we go. We've done a nice little approximation, and we've got our omega. And now we have a plus or minus. That means we have two solutions, one for S plus and one for S minus, where we have an omega in the plus direction and an omega in the minus direction. And so we look for those two arbitrary complex constants, and our two solutions are omega plus and omega minus. So let's now make the radical choice that S plus or minus is the same thing, and we're going to call it A over 2. Why? It becomes convenient. And that's just some arbitrary real valued constant like 1 or 2, not 1 plus 2i. Now when we put this all together, we get this crazy looking thing, which is s equals a, which is, we don't care about that constant, it's just some constant is equal to e to the I, that's a power then, minus I omega sine lambda times t. And that's important, because there's the sine lambda is its own constant, right? So omega t is the real thing. It's not sine of lambda t, it's sine lambda omega t. I guess I should have written it like that, but this is pretty typical what you'd see. And we got that cosine on the outside. That's not part of the power. So where did this come from? All right, so real quick, where that came from is I just plugged in those solutions into this equation. We see there's the omega plus, and we see the omega minus, and then we've collecting the like terms, because we can extract out the I omega sine lambda t out of both of them, and we're left with an I GLT in the positive direction and I square root GLT in the negative direction. And funny enough is that e to the I theta is actually a trigonometric solution, and you can break out e to the I some value equal to cosine of that value plus I sine of that value. And that's what's happened in the third line of this thing. So we've got because cosine of some angle plus I some angle, the same angle, is equal to e to the I of the angle, which is a really interesting little identity. Go look it up if you like. That's where that comes from. That's a trigonometric relationship, which is a lot of fun. And this is a really good thing to use from complex analysis. It's very helpful for the algebra because these things are identities that come from complex algebra, I should call it, where you use the imaginary numbers as your guiding tool. And they're just as valid as any other number, just like pi or 0 or 1 over 12 or whatever. Negative I is a valid number, and you can do algebra on it. All right, so we collect like terms, and notice that the cosine of a negative theta, a negative angle, is the same as the cosine of the positive same angle. So we just add those together to get twice of those. And then we extract out the I sine, and we find that, wait a second, we have I sine minus I sine, and those things are, oh wait, the negative of a sine is the same as the positive of a sine, because the sine of an angle is going to be, if you take the negative of the angle, you get the sine of it becomes the negative sine, right. Sine of the negative angle is the negative of the application. So we go up, right? So if you take the sine of an angle is either up, and if it's negative, it's down, but the sine would be positive or negative as a result, and so sine of negative theta equals negative sine theta. That's how that works, because we're going the opposite direction around the circle. So those two last things cancel, and we're left with what we showed before. Okay, great. Now we remember, go all the way back and say, oh, wait. S equals x tick plus I y tick, because we're looking in Cartesian coordinates, not all this stuff with complex coordinates and so forth. We want to get it to the function x and y as a function of time and a function of the angular frequency that the plumb bob is going back and forth on. So let's plug plug x and s back into this thing. Remember that s is equal to this x and y. But notice that e to the I some angle is cosine of an angle plus I sine of an angle. And by gosh, there it is, we've got that, which is exactly what we had before. So we've got x and y sticking out right there, that to both of us. So we got x equals cosine. I should have put big parentheses in there, because it's not just a cosine theta comes up plus the second one. There should be big parentheses enclosing both the cosine and this I sine function there, because I broke it apart. So that's a terrible typo. I really wish I could fix that, but off we go anyway. So x is equal to the cosine part and y is equal to the sine part. And now we see we've gotten that they're nearly identical. So these two equations describe sinusoidal oscillations in a plane that's normal to that's normal to the Earth's surface, and whose the plane is always up and down with respect to the Earth's surface, and has a standard pendulum frequency of GL over T. That's the normal pendulum frequency that if you were to solve, oh wait, ignore everything about the Coriolis effect. That's what you'd get if you did this entire analysis. Oh, very simple. The Coriolis effect, though, however, plops that cosine or sine of omega sine t, so sine lambda times t. So the omega, once again, remember, is the angular rotation of the Earth now. So that's where omega comes in here. So we lost that little omega because that was the sinusoidal frequency of the plumb bob. We're not too worried about that. We're worried about the position of x and y now. So the period of the precession, and the plane precesses around its axis. So that means the plane slowly shifts the orientation of x and y. It'll always change a little bit in x and a little bit in y after some time. So how long will it take? Depends on the latitude. The period of the precession, meaning how long does it take for the plane to rotate completely around, is 24 hours divided by the sine of the latitude. So the pendulum oscillates in the x direction, north-south. Let's say we've got this pendulum oscillating in the x direction, north-south, and in the y direction. And after the period divided by 4, it will be rotated in the y direction, east and west. And then it'll be back in the x direction. At period equals halfway around. And then at period 3/4, it'll be, the plane will have oscillated back to the x direction, x to y direction. And then one full rotation later, it will be back to the original orientation. So this precession is clockwise from the northern hemisphere and counterclockwise in the southern hemisphere. So the change in the direction that the plumb bob is going, it basically means that if you have a pendulum and you start it swinging and you don't move at all and just stand there for hours, and this is a proper Foucault pendulum, after a while, what'll happen is, if you're in the northern hemisphere and you just let that pendulum go and you're standing, you're the one who pulls it towards you, and then you let it go and you stand there and simply wait. Because it will rotate clockwise as seen from above, then what'll happen is the plumb bob will start to slowly come towards you, but then miss you to the left. And then it'll keep missing you more and more and more to the left. It'll keep arcing more and more to your left. And eventually, if you stood there long enough, say 24 hours, more than that, much longer than that at higher latitudes, but at the poles it'd be exactly 24 hours, and it's longer and longer and longer as you get closer and closer to the equator. But the mid latitudes, it's pretty long, but you'll actually be able to measure it over the course of a day if it's a proper Foucault pendulum, meaning there's no friction on the attachment to the roof, and there's nothing getting in the way. And if it happens to be in a museum, which a lot of these are, which there's a bunch of these that exist all over the world, and there's no kids getting in the way, nobody jumping in the way, nobody's messing with it, and maybe even you've enclosed it in a vacuum chamber. Maybe you've gotten rid of all that stuff. Maybe you've even put it in a dark place so that there's no effective heat on the inside for changing its direction due to heat or wind or anything. So this actually happens, and it's due to the Coriolis force effect, which is due to the Earth rotating. So as the Earth rotates, we get this slight change with the plumb bob at the northern hemisphere. Goes more, when it comes towards you, goes more and more and more to your left. And eventually, it comes all the way around, which is pretty cool. This was first devised in 1851 by Foucault, and to this day there is an exact copy in the Pantheon in Paris where Foucault actually set this up. It was moved to a different location for a long time, many decades, and moved back to the Pantheon, but the actual original plumb bob that Foucault made fell and broke in, I believe, 2005 or 2010. You go look it up on YouTube to see where it actually broke. But I believe that it's on display in the Pantheon there alongside this exact replica. So if you go and check it, you can see where it is. You can see what the movements of it, and you'll notice that the wire that it's hanging from is very straight, it's very light, and the bob does not appear to move very much, and that ceiling is very tall compared to the area that it's swinging across. So that's what we mean by a small orientation, and this is obviously it's at rest. It's not swinging, of course. But it's important to know that this is one of our big proofs that shows that A, the Earth is round. because you can put this, the period of oscillation is different for different latitudes, and B, the Earth is rotating. So this is a really important discovery that can only be, that is best explained. Now, you can make up any kind of crazy mathematics you want, like flat earthers do. They make up a lot of crazy stuff. But we try to go for the simplest solution that works and that fits everything, and where you don't have to have ad hoc things going left and right in order to keep your idea alive. That's the problem with the flat earth people, is that they don't basically know when to give up. Or more specifically, you gotta hand it to their tenacity, because they'll just keep making stuff. But I don't see why they bother, because it's more and more and more and more complex, everything they do. It's a lot easier just to say that the Earth is round and it's rotating, and that's very simple. It makes the explanation simple, it makes the thinking simple, and it fits so many observations, and it also allows us to predict things that we otherwise couldn't predict. And so this is one of many things that helps us understand that the Earth is round, and of course if you see it from space, like the astronauts did this from the Apollo 8, you definitely know that it's round. And this will round out, as it were, our discussion of rotating reference frames. Thanks so much for joining me.